Similarly, there is something that governs voltages in general. Okay. So let's say you have an electrical circuit. Electrical circuit means that there is some loop of electrical components. Now we have not even discussed any element, but I will take some two terminal elements 1, 2, 3, 4 and 5. Okay. And I will measure the voltage across each one. Like I said, voltage is potential difference between 2 points. So here I will measure V1 in this direction, and here I will measure V2 in this direction. Please mind the directions in which I am writing this. V3 here, V4. You see that I am taking all the differences in the same direction, and V5. Okay, again, this has nothing to do with the specifics of the circuit, and there is a law that says that V1 plus V2 plus V3 plus V4 plus V5 equals 0. Okay, and this is known as so it appears that the audio was broken. What I was talking about was the sum of voltages around a loop being 0. So here I have shown it for this particular circuit, V1 plus V2 plus V3 plus V4 plus V5 equals 0. That is, sum of voltages around this closed loop is 0, with all the voltages being defined with a consistent polarity. Okay, you see that they are all in the same direction around the loop. And this is known as Kirchhoff's voltage law. The response I would like from participants is to tell me the conditions under which this is true. Again, I have got a number of responses. Okay. Now, some of you said that it is true in a closed loop. Yes, of course, it's only the closed loop that I am discussing, right? Here I have written a loop, and as I have written on the side, sum of voltages around a closed loop equals 0. So my question is that violated in some condition? Okay. Now it turns out that it can be violated if there is significant time varying magnetic field cutting this loop. Okay, so this loop has certain area. So this loop can enclose certain time varying magnetic fields. If there are time varying magnetic fields in the cutting the loop, then the sum of voltages doesn't have to be 0. Okay. So again, all the practical situations, or most of the practical situations that we encounter, the time varying magnetic fields cutting this loop will be small enough, cutting our loops will be small enough that we can take the sum of voltages to be exactly 0. Okay. Okay. So again, this turns out to be true in practice in a lot of cases. So we can use the Kirchhoff's voltage law also safely. Okay. Now, there are some people asking questions on what happens if voltages are induced from other loops. That's exactly what I'm saying, that if there are time varying magnetic fields, there will be the sum of these things will not be zero. It will be related to the rate of change of magnetic field and the area of the loop. So we will not consider those conditions. We will only consider the condition where the uh, flux is zero. That is time varying flux cutting time varying magnetic field cutting the loop is zero. Okay. Okay. So we have these two basic laws. And Kirchhoff's voltage law and Kirchhoff's current law. One relates to voltages in a loop and one relates to currents in a loop. And one of the very important things while applying this is to apply it with a consistent polarity. Okay. So here I will show a loop. The loop will have some elements, but I will not worry about those, or maybe I will show it with elements so that there is no confusion. So if you look at this, what I've done is to go this way. Okay. If I go in a clockwise loop, I always have minus first and plus next and so on. Okay, in the direction, in this direction. Okay, I'm always going in this direction, and then I sum all the voltages, it becomes zero. Similarly, for Kirchhoff's current law, at a node, the sum of all currents flowing out of a node is zero. So I suggest that right from the beginning you adopt a consistent polarity, because if you make a mistake with the polarity of these things, obviously you will get the wrong answer. Okay. Now one thing I have to mention about voltages, I did this for currents. That is, I told you that a current 1 ampere flowing from A to B is exactly the same as a current of minus 1 ampere flowing that way. And similarly, if you have 2 points, let's say X and Y, and having a 1 volt difference in this direction is exactly the same as X and Y, and I will measure Y with respect to X. Okay, the voltage in this direction being minus 1 volt. Okay, so this is just so that you are comfortable with the sign convention. So again, for instance, I could have some 2 points and I will write V1 this way. This does not necessarily mean that this is at a higher potential than that. It says that it is higher by V1, and V1 itself could be positive or negative. Okay. Okay, so I think in today's lecture we have discussed a number of things, basically definitions of voltage and currents and the laws governing them. Okay, now we will continue from here in the next lecture. There were a couple of more questions. Some of them are related to frequency of the voltage and so on. I will not discuss those things here as they are not really relevant. Okay, because even if let's say V1, V2, V3, V4 and V5 are time varying, Kirchhoff's voltage law says that at every instant of time, the sum of those things has to be zero. Okay. Similarly, for the currents, now the sum of currents I1, I2, I3, I4 is zero for this particular example here. Okay. now this is true even if those currents are time varying. They could in general be time varying. At every instant of time, the sum has to be 0. Okay, so that's the meaning of Kirchhoff's voltage and current law. Now there is one very interesting question, which is, what are the circuits that do not obey Kirchhoff's voltage law or current law? Okay, are there common examples? Now, it turns out that there is, first of all, so there is one very common example, which is basically, if the dimensions of your circuit are very large. Now, by very large, what do I mean? Very large compared to the wavelength of the signal, then these things do not hold good. Okay, we can perhaps elaborate on this later. What I mean by that is, let's say I have a really long wire. Okay, and again I will think of positive charges flowing this way. Now, always we think of charges flowing instantaneously, but we know that it really moves at the speed of light. Okay, at least it is limited to the speed of light. It can only move slower than that. Now, let's say that you drive a current and you reverse the direction before the current can get from here to there. Okay, because there is always some length to the wire, and then it takes some time to get from here to there. And before that, if you reverse the direction of the current, so let's say you are driving a current from one side, we will not worry about how to do it. Before it gets from here to there, the charge gets from here to there, you reverse it. Then you look at different parts of the wire, they will be carrying different currents. Okay, and a very common example of this is the antenna. I think all of you are familiar with antennas, which are just a single wire sticking out. It could be sticking out of your radio or your car. It's just sticking out, and you will drive a current into it. It looks like it's just hanging in the air, and then current is going into it. So clearly, Kirchhoff's current law is not valid here. What really happens is that the length of the antenna is comparable to the wavelength. That is, before the current reaches from one end of the antenna to the other, the direction of the current driving it changes, and then so you have a consistent situation without Kirchhoff's current law being violated. Okay. Now we will only be talking about those situations where the dimensions of the circuits are much smaller than the electrical wavelength of the signals that are driving it. So in our cases, Kirchhoff's current law will be valid, and similarly for Kirchhoff's voltage law. So in general, these things can be violated if you have a very large circuit and large relation to the electrical wavelength, or in general if you increase the frequencies of the signals. Okay. Any questions? Okay, so there are some general questions which we will deal with later. So in the next lecture, what we will do is take some electrical circuit elements which are commonly used, discuss their relationship between voltages and currents. What we did today was to see general properties of voltages and currents and their definitions. Okay, so in the next lecture we will look at some elements and then make some simple circuits out of them.